Hello everyone, my name is Taiga Hiroka. In this talk, I talk about certified everlasting zero knowledge proof for QMA. This work is joint work with Tomoyuki Morimae, Nishimaki, and Takashi Yamakawa. First, let me explain QMA briefly. Roughly speaking, QMA is a quantum version of NP. In this class, a quantum polynomial time verifier can check whether the instance X is S instance or not. First, the verifier receives a witness psi, and he checks whether the instance X is S instance or not. When the instance X is S instance, there exists a quantum witness psi such that the verifier accepts with high probability. On the other hand, when the instance X is no instance, for all quantum states psi, the verifier rejects with high probability. If the language L satisfies these properties at the same time, we say that the language L is in QMA. In this talk, I'll consider zero knowledge proof for QMA. In the zero knowledge proof for QMA, a quantum polynomial time prover with a quantum witness psi can convince a verifier that the instance X is S instance without revealing any information beyond the fact that the instance X is S instance. Broadbent and Grillo have constructed zero knowledge proof for QMA from classical commitments with statistical binding and computational hiding. The outline of the construction is as follows. First, the prover randomly generates in-length classical bit strings and commits them using classical commitments with statistical binding and computational hiding. Then, the verifier randomly generates I and sends it to the prover as a challenge. Then the prover sends the ith bit of A to the verifier. The verifier checks whether the instance X is S instance or not. Their construction satisfies the following three properties. The first property is completeness. This guarantees that when the protocol is executed honestly and the instance X is S instance, the verifier accepts with a high probability. And the second property is statistical soundness. This guarantees that when the instance X is no instance, the verifier rejects with high probability for any unbounded malicious prover that tries to make the verifier accept. The third property is computational zero knowledge. This intuitively guarantees that no quantum polynomial time malicious verifier learns anything beyond the fact that the instance X is S instance. Now, I will explain our motivation. Although zero knowledge proof for QMA satisfies these properties, computational zero knowledge has a risk. In fact, new algorithms or improvements of computers may solve the problem, underlying the security of computational zero knowledge. So, computational zero knowledge does not necessarily imply long-term security. In other words, malicious verifier may obtain information beyond the fact that the instance X is S instance in the future. So this is undesirable. One way to resolve the problem is to use zero knowledge proof for QMA with statistical zero knowledge. In a protocol with statistical zero knowledge, the security holds against unbounded malicious verifier. So the security will never break in the future. However, it is believed that we cannot construct zero knowledge proof for QMA with statistical soundness and statistical zero knowledge at the same time. So, if the protocol satisfies statistical soundness, zero knowledge property must be computational one, and thus a malicious verifier may obtain information beyond the fact that the instance X is S instance in the future. So our question is as follows. Can we construct zero-knowledge proof for QMA where the zero-knowledge property holds in a long term without compromising statistical soundness? Note that this question was originally posed by Broadbent and Islam in TCC 2020. In our work, we resolve this question affirmatively. For that, first, we introduce a new notion of zero-knowledge property, which we call certified everlasting zero-knowledge, and then construct zero-knowledge proof for QMA with statistical soundness and certified everlasting zero-knowledge at the same time. Now, I will explain an intuitive definition of certified everlasting zero-knowledge. In a protocol with certified everlasting zero-knowledge, a malicious verifier can issue a certificate which shows that he deletes the information received from the prover. The prover can check whether the certificate is valid or not using her internal information. When the certificate is valid, she accepts the verifier, and otherwise rejects the verifier. When she accepts the verifier, even if its computing power becomes unbounded after that, he cannot obtain information beyond the fact that the instance X is yes instance. This is the intuitive definition of certified everlasting zero knowledge. So, in the certified everlasting zero knowledge, the security will never break in the future when the certificate is valid. Note that certified everlasting zero knowledge does not guarantee any security when the certificate is not valid. However, the prover can prevent the verifier from refusing to output a valid certificate by penalizing the malicious verifier. So we believe that this security is still meaningful. Now, I will explain our construction of certified everlasting zero knowledge proof for QMA. For that, I will explain why the known construction is not secure against unbounded malicious verifier. In the known construction, classical commitment satisfies only computational hiding. So unbounded malicious verifier can obtain the committed value from the classical commitment. This fact breaks the zero-knowledge property of the known construction. To resolve the problem, in our work, we introduce a new quantum commitment with a new hiding property, which we call certified everlasting hiding. In this hiding, a malicious receiver can issue a certificate which shows that he deletes the quantum commitment. When the certificate is valid, even if receiver's computing power becomes unbounded after that, he cannot obtain the information of the committed value. In our work, we construct quantum commitment with statistical binding and certified everlasting hiding from an ordinary classical commitment with statistical binding and computational hiding in the quantum random oracle model. Now, I will explain an informal construction. Note that this is not a formal construction for ease of understanding. So if you are interested in a formal construction, please see a paper. First, in a construction, the sender randomly generates two classical bit strings and keeps one as a secret key and the other as a verification key. Then, the sender generates BB84 states according to these classical bit strings. The base of these quantum states depends on the secret key. If the secret key is equal to 0, the sender generates computation basis states. On the other hand, if the secret key is equal to 1, the sender generates adamant basis states. And the bit values of these quantum states is equal to the verification key. Then, the sender encrypts message M using the bit values of computation basis states as follows, where H is a hash function. Then, the sender encrypts the secret key using a classical commitment with statistical binding and computational hiding. Then the sender sends them to the receiver as a commitment of the message M. Our construction satisfies correctness. This guarantees that when the protocol is executed honestly, a receiver can obtain the message M correctly. When the receiver want to recover the message M from the commitments, he requests her to send the secret key. Then the receiver checks whether the secret key is equal to the committed value or not. Now the sender behaves honestly, so the receiver accepts with an overwhelming probability. Reminds that the secret key is the base of these quantum states. So by measuring these computation basis states in the computation basis, he can obtain 0, 1, and by computing its hash function, he can recover message M correctly. And our construction also satisfies statistical binding. This statistical binding intuitively guarantees that no unbounded malicious sender can change the probability distribution that the receiver obtains message M. Now I will explain intuitive reason why our construction satisfies statistical binding. And a malicious sender tries to make the receiver accept the different secret key other than the sender first committed. However, even unbounded malicious sender cannot change the secret key since the classical commitment satisfies statistical binding. This fact implies that the secret key used to extract message M from this part is determined only by the commitment. So even unbounded malicious sender cannot change the probability distribution that the receiver obtains message M after she sends the quantum commitment. This is the intuitive reason why our construction satisfies statistical binding. And our construction also satisfies certified everlasting hiding. In this hiding, a malicious receiver can issue a certificate which shows that he deletes the quantum commitments correctly. If the certificate is valid, even if its computing power becomes unbounded after that, he cannot obtain the information of message M correctly. When the sender wants to delete the quantum commitment, she requests him to measure all these quantum states in the mad basis and receive the measurement outcomes as a certificate. Then the sender checks whether the certificate is equal to the verification key or not, and whether the secret key is equal to 1. If so, the sender accepts the receiver, and otherwise rejects the receiver. When the sender accepts the receiver, even if its computing power becomes unbounded after that, and the secret key is leaked from the sender, he cannot obtain the information of message M correctly. Intuitively, this is what certified everlasting hiding guarantees. Now, I will explain the intuitive reason why our construction satisfies certified everlasting hiding. When the receiver's computing power is limited, he cannot obtain the basis of these quantum states from the commitments, since the classical commitment satisfies computational hiding. So, in order to make the sender accept with a high probability, he has to measure all these quantum states in the mad basis. On the other hand, if he measures these computation basis states in the mad basis, these quantum states collapses to random classical bit string, and he can no longer obtain the bit values of computation basis states, even if its computing power becomes unbounded and he obtains the basis of these quantum states. So this is the intuitive reason why our construction satisfies certified everlasting hiding. Once we have constructed quantum commitments with these properties, we can construct zero-knowledge proof for QMA by combining the non-construction of zero-knowledge proof for QMA on Broadband and Grillo. The outline of our construction is as follows. First, the prover randomly generates n-length classical bit strings and commits them using our new quantum commitment. Then, the verifier randomly generates I and generates a certificate of the quantum commitment other than this I. Then the verifier sends them to the prover. The prover checks whether all certificates are valid or not using internal information. Then the prover sends the ith bit of A to the verifier. The verifier checks whether the instance X is S instance or not. Our construction satisfies the following three properties from the construction of Broadband and Grillo. And our construction also satisfies certified everlasting zero knowledge, which is the main target of this work. Now, I will explain intuitive reason why our construction satisfies certified everlasting zero knowledge. From the certified everlasting hiding of our quantum commitment, when the certificates are valid, he cannot obtain the committed value from the information received from the prover. So he cannot obtain information beyond the fact that the instance X is S instance. This is the intuitive reason why our construction satisfies certified everlasting zero knowledge. In our work, we have constructed certified everlasting zero knowledge proof for QMA by using quantum mechanics. Note that quantum mechanics is essential for our construction. Finally, I will explain the reason why quantum mechanics is essential in the next slide. In the classical world, certified everlasting zero knowledge implies statistical zero knowledge. So in the classical world, we cannot construct certified everlasting zero knowledge proof for QMA or NP. Now I will explain the reason why certified everlasting zero knowledge implies statistical zero knowledge in the classical world. For that, we will consider zero knowledge proof with classical prover and classical verifier. Then, messages between them are also classical. So the malicious verifier can copy the information received from the prover, since these are classical bit strings. So by measuring the copied information, he can issue a valid certificate. And from the definition of certified everlasting zero knowledge, when the certificate is valid, his computing power becomes unbounded. And even though he cannot obtain information beyond the fact that the instance X is S instance. On the other hand, unbounded malicious verifier can access to P1, P2. So these must be secure against unbounded verifier. So in the classical world, certified everlasting zero knowledge implies statistical zero knowledge. On the other hand, in the quantum world, the same discussion does not go through. This is because in the quantum world, even malicious verifier cannot copy the information received from the prover, since the quantum no-cloning theorem holds in the quantum world. So in the quantum world, certified everlasting zero knowledge does not necessarily imply statistical zero knowledge. Now, I summarize this talk. First, in our work, we have introduced a new notion of commitments with statistical soundness and certified everlasting hiding, and have constructed. Second, we have introduced a new notion of zero knowledge property, which we call certified everlasting zero knowledge, and then construct certified everlasting zero knowledge proof for QMA. Open problems are as follows. The first question is, can we construct other cryptographic primitives with certified everlasting security? Note that recent follow-up research make progress in this direction. Batsek-Krana have constructed public encryption, Fourier homomorphic encryption, and so on with certified everlasting security. In our recent result, we show that we can construct functional encryption for NC1 circuits with certified everlasting security. But the number of key query is a priori bounded. And the second direction is, can we define a different type of everlasting security and construct a protocol with a security? In our work, we have defined a certified everlasting security where computation assumptions are required only before the valid certificate is issued. On the other hand, we may be able to define a different type of everlasting security where computation assumption is required only temporarily, but it remains open. Now I finish my talk. Thank you for listening.